binomial expansion looks a little bit like this. And we need to know how to expand it to solve different problems. Technically, you need to know how to solve problems by using binomial theorem. Students in my class, or Kate's class last year, were exposed to a video that demonstrated the binomial theorem, which we covered after we did probability. Either way, I just wanted to show you that in this thing here, which you have access to on Google Classroom, your learning schedule, under binomial expansions, I've got here in class, we are focusing on Pascal's triangle methodology. This video, however, will take you through the binomial theorem. Okay, so that video effectively demonstrates how to use the binomial theorem in order to be successful. Okay. All right. So I'm going to focus on Pascal's triangle because 9 times out of 10, Pascal's triangle is sufficient in order to solve most problems. P.S. What I've started to do, you tell me whether it's useful or not, but what I've started to do is rather than putting in page numbers, which kind of doesn't always work because we're using 2 different versions of the book, I've started putting links to the online textbooks. If you've got the online textbook, if you click on the link, it'll take you to the particular section. Yeah, I hope it's useful. So I'm going to continue to do that because I think it's useful for those using the interactive one. For those who are using the textbook, I keep on stuffing up the page numbers because of the old and the new textbook. I'm not going to put page numbers on anymore. You know, you just have to follow your own way. You're old enough and bad enough to sort that out yourself, I think. But I thought that might be a bit useful. Anyway, I'm glad I captured it on video. That was useful as well, wasn't it? Okay, back to this. So I just downplayed binomial theorem and said, oh, well, you know, Pascal's triangle works all the time, blah, 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 blah. I'll tell you this now. For basic problems, Pascal's triangle is almost always the easiest until you get to n equals 5, 6, 7, 8, 9, 10. Even 5 is okay. When you start getting beyond 5, you know, Pascal's triangle is a pain in the bum. Secondly, there are a heap of complex problems, even for a power of 4, that could be asked, which binomial theorem will allow you to solve it most efficiently. So I'm saying that as a bit of an upsell for binomial theorem as well. Although we don't have time to actually cover it thoroughly in class, like to do it justice would need a whole lesson kind of thing by itself. We just don't have that time. If you do have the opportunity to, and you want to be working at that sort of A standard, most efficient way, watch the video on binomial theorem, practice using the binomial theorem, ask me questions in class when you can, see me after class if you want, you know, otherwise. But yeah, if you get across binomial theorem, you'll be able to efficiently solve all expansion kinds of problems. But Pascal's triangle will do for the kind of problems you're going to encounter in tests and exams for this course. Not the most efficient method, but it gets you there fairly quickly with a bit of blood, sweat and tears. So I'm going to assume that you remember by Pascal's triangle and how it works. And I'm going to give you, I've got an example here of a more complex problem. I think this problem might be on the assignment. No, I don't think it is actually. But I have seen this kind of problem in past tests. I haven't seen whether it's on the progress test that's coming up next week. You should know about that. It's on the schedule. And or maybe it's on the end of unit test as well. I'm not sure, this kind of problem. That's why I'm doing it. But nevertheless, the practice problems are mostly just going to be using Pascal's triangle to expand. But anyway, so the first 2 terms of ax plus by to the power of 4 are 16x to the power of 4 minus 19x cubed y. Find a and b. So what we're going to do, I'll just keep that zoomed out, is I'm going to do it not too slowly, but I'm just going to remind you how Pascal's triangle works as I go along. So the first thing you have to do is generate Pascal's triangle, which if you remember starts with a triangle of ones like that, 1 and then 1, 1. And then we generate the next row by adding the numbers above it and putting ones on the end. So I go 1 on the end, 1 and 1 is 2, and then 1 on the end. 1 on the end, 1 and 2 is 3, 2 and 1 is 3, 1 on the end. 1 here, 1 and 3 is 4, 3 and 3 is 6, 3 and 1 is 4, and 1 on the end. And I could keep going if I wanted to. You can generate Pascal's triangle pretty quickly. So that's why it's good for, like you can imagine if it was to the power of 10 and you're having to go all the way to the 10th row. By the way, we call this the 0th row. So 0th row, first row, second row, third row, fourth row. And then the other thing I just wanted to point out to you, and I'm just doing this just for the notes, is that if you've got this sort of expansion here, a plus b to the power of n, then a starts at power of n and goes down to the power of 0, which effectively means it disappears. And the second term starts at b to the power of 0, which effectively means it's not there, and goes up one at a time to b to the power of n. That's how that works. So to solve this problem here, I don't have to do a full expansion because you can see it's just saying the first two terms are 16x to the power of 4 minus 96xy cubed. So what I can do is I can basically match up what I know with what I'm given. So what I'm given is 16x to the power of 4. 16x to the power of 4. And from my Pascal's triangle expansion, I'll just be a bit more explicit for this. I've got 1, the starting coefficient from that row, 14641, multiplied by, and then I take the first term, which is ax, and raise it to the power of 4 because this is n equals 4. Okay, I'll simplify this by saying, well, 1 times anything is just itself, and ax to the power of 4 is a to the power of 4, x to the power of 4. Now, I'm not going to write this down just for time's sake, but what I'm going to do now is I'm going to equate the coefficients. So the powers of x are the same, and so I take the coefficients of x to the power of 4 and I equate them. So I say a to the power of 4 is equal to 16. That's equating coefficients. Therefore, a is equal to plus or minus 2. Okay? If it was an odd power, I could just say positive 2, but it's an even power, so it's plus or minus 2. Give you a moment to sink that in, and then I'll go to the next page where there's a bit more room. So we do the same thing with the next one now. So I'm going to let a equal, so given that a equals 2, I would have the next one would be minus 96x cubed y. That's what we're given. And using my Pascal's triangle expansion, the second starting coefficient is 4. So it's 4 multiplied by 2x. I replace the a with a 2. 2x to the power of 3 because we've gone down a power. And we've multiplied that by by, the second term, to the power of 1. But I'm not going to write the power of 1 in. Okay, simplifying that, I'm going to have 4 multiplied by 8 x cubed multiplied by by. And then equating coefficients again. So I'm literally taking the minus 96 from here and the 4 and the 8 here. Oh, and the b, sorry. And I'm going to get minus 96 must be equal to 32b. And everyone knows their 32 times table. So if I divide both sides by 32, you're going to get b is equal to negative 3. And just to save time, if I went for a equals negative 2, I'd end up with b equal to positive 3. For reasons that may be obvious to some of you, and for the others, don't worry about it too much. If it's not obvious to you, you could substitute a equals negative 2 in and then work out the other value of b. So that's basically it. That's a more complex example because, you're not doing just straightforward expansion. You're trying to solve a problem with a's and b's in it and so on. But the methodology is the same. We're using step 1, generate Pascal's triangle to the appropriate row. Step 2, use our knowledge of Pascal's triangle to complete the expansion or to solve the problem. And we're done. So I'll leave the video there.